Okay, let's get started. So we're very happy to have Pierre Deligne talk about zeros of characters.
Thank you. So I will first state the theorem I want to explain. It's a theorem of Serre with some complement due to me. So here is it. Take a complex reductive group. And by reductive, I include connected. So you can think GLN over C. You can think VLN, SON, SVN, or more exceptional groups. And I care about irreducible representation, meaning the algebraic sense. So algebraic map from the group to GLN. I want them to be irreducible, and I am interested in the character of such an irreducible representation. And I assume that the dimension of the representation is not one, meaning the value of the character of the unit element is not one. Then what one asks, that there exists an element of the group, often, so Gn equals the unit element for some n, on which the character vanishes. And the complement, so that's due to Serre, and the complement due to me is that one take n, one can find G so that the order is a prime power. Now, there are a number of variants. For instance, this is completely equivalent to the same statement if you take a compact Lie group and an irreducible character of dimension not one complex and same conclusion. And essentially, to go from complex reductive to compact, it's the Weil unitary trick that you have a maximal compact, everything happens for the maximal compact subgroup. Ordinary representation of the compact subgroup are essentially the same thing as representation of the complex group. Now, a number of variants has been obtained by Serre with some devices. So the statement is true, in fact, for any linear algebraic group, connected or not. And essentially, one has to combine this statement with statements about finite groups. And things that are very nice for the statement just wanting some Dawson element in the group, because then one can use theorems of Verdun and Burnside in the 18th century and of 1903. For the case when one wants something power of a prime, there are claims in the literature about finite groups, which suffice to get it from this, but the literature is in a terrible state, so it is a correct proof of this, assuming some claim for which there is no published proof. So that's frequent in the theory of finite groups. Now, because I like it very much, I will tell one ingredient for going from this case to the general case of linear algebraic group, the case where G is finite. Then this statement that some element of group vanish somewhere, it's a theorem of Burnside. Because I find the proof very nice, I will explain it. A final group, I take a character of a irreducible representation, not of dimension 1, and I want to prove there is a 0. Let me first consider the case where the character is with rational value. And then it's of course also integral value, because the value are anyway sums of roots of unity, so algebraic integer, so if rational it's an ordinary integer. Then one just has to use the orthogonality of character. Which means that the mean value of the absolute value of square of k of j is 1. And those are all integer. Now, if you have family of integer and the mean is 1, then if 1 is bigger than 1, some has to be smaller than 1. And I assume the dimension is not 1, so at least that the unit element is corresponding sum is bigger than 1. So I conclude that for some v, k of v bar is smaller than 1, and then one used the fundamental theorem that if an integer is positive of 0 and is strictly smaller than 1, then it is 0. Now, this does not just as well in the general case, because then it can very well happen that some absolute value of the character will be smaller than 1, but it's just an algebraic integer. This will tell nothing. So what one has to do is to group together the element of the group which span the same cyclic subgroup. So let me look.
Why is it clear that this element will have the property that G to the n is the identity? Does this follow from the fact that it has rational?
Because it's finite group.
Ah, okay.
Yes, no. Otherwise, so for finite group, that's this term of Burnside. In the general case, it's trivial that it vanishes somewhere, but it's strange that it vanishes. In general, if you have a function on a group or on a torus, it needs an explanation why it vanished at some certain point. So the point will give some explanation of why it happened sometime. Now, if I look now at the generality of any character and I group together the one generating the same cyclic group, let's take one element and look of order n, and I look at all the GA for A prime to n. This is the group of elements, the set of elements I want to consider together. Then G will have some eigenvalue, which are some roots of unity, and even nth root of unity because 0 to the power n is 1. And the value of the character is the sum of those eigenvalue. If I replace G by G to the power A, I will get the eigenvalue at the power A, and I look at now this sum for the value of the character on this other element. Now, what is nice is that this and this are Galois conjugates, because if we are in the cyclotomic field of nth root of unity, the action of Galois is raising root of unity to the a's power, nth root of unity to the a's power. So I can tell that it is Galois acting on the first. So this is curve G, and the other one are conjugates. Now, if I now take the, yes, and I have the same kind of statement and for K of V times K of G bar, just, we just gain here that this is something positive. Now, if I take the product of the absolute value square of the K of G for one such length of element, this is a norm from the cyclotomic field. A norm from cyclotomic to Q. And so this is an integer. And it is at least 0 also because each term is positive or 0. Now, if this integer is 0, we are very happy. We have proved that the character vanishes everywhere Serre. But now what one uses is the relation between arithmetic and geometric mean from the fact that if it's at least 1, then the same holds for the sum of the, but if I have bigger than 1, then the geometric mean is bigger than 1 also, and then the arithmetic mean is also at least 1, because arithmetic is bigger than geometric. And now one can again take this argument. One has all those bunches. Bunch by bunch, the mean value is at least 1. So if somewhere you have something bigger than 1, you must have something smaller than 1, and it's the same argument as before. Okay. Now I will start the proof of the theorem. Yes, I would say that the reason I explained this theorem of Bernstein is that in some sense it's also a motivation for the theorem for any linear algebraic group. But that is, one cannot use at all the same method. Now I will need to explain the story of Wood's weights for a reductive group, and then afterward the well-character formula to start the proof. So first some reminder about roots and weights. And to the right side of the blackboard, I will tell what things mean in the case of GLM. So one fix a maximal torus, meaning an algebraic subgroup with multiplicative group C star at some power. And here it means one can take two diagonal matrices. Now, in fact, it's enough to understand the character on T, because T and all its conjugates fill essentially the group. Or I could also say that any element is a product of something conjugate to something diagonal times a commuting unipotent. So the story will take place essentially on the torus, so here essentially on diagonal matrices. And I will need a formula for a character on the diagonal matrices. Now, as I was telling, this torus is multiplicative group at the power n, meaning group of points C multiplicative X power n, and one has to consider the group xt of weight, which is the group of homomorphism from T to the multiplicative group. So in this case, you have a diagonal matrices A1, AN, and you look at map to the star of the form A1 and 1, A2 and 2, 2 AN, so and N. So in this case, this x of t is just the n. If I had A for the diagonal matrices, and if I have lambda in the n, this I will write as being A the power lambda, so product of AI and I. And in part because of this, this is, of course, a group is amorphic to the n for some n, and the multiplication I will write it additive. So if I have lambda in this group, I will write t to the power lambda for the value of this character on t. So that's just like what's happening for VLN. Next, one has to introduce the roots. One looks at the advent action of the torus on the Lie algebra on the group, and it decomposes as the Lie algebra of T plus some of eigenspaces alpha. And on a given eigenspace, T will act by multiplication by some character, and those set of characters is what one calls the root. So in the case of ELN, the Lie algebra is n times n matrices. The Lie algebra of T is anything diagonal, and G alpha are the thing which are zero everywhere except at one place, IG, and then if it is at the place IG, the corresponding root is AI AG minus 1. Now, there is a dual side to this story, which is to introduce the dual of T, which is the homomorphism from GM to the torus. So in this case, I look at up to the torus of GM to the torus of the form U going to U and 1, U and 2, U and N. So here, it's again, of course, it's the same dimension. It's a Zn, and that's the dual Zn. And in it, we have the coroots, which are the following thing. I'll explain it for GLN first. Each time you have a root, you can look the opposite root, where instead of something at the place IG, you have also something at the place GI. And then you can look at the element of, you have a SL2 in GLN, which is all matrices A inverse, here, something, one on the diagonal and 0 elsewhere. So you have this two-dimensional subspace spanned by the vector AI and V, and you have a corresponding SL2 contained in GLN. So you have the same So in general, for each fruit, you have SL2 or in the algebra you have a SL2, in the group you have a SL2 or PSL2, which is attached to the root. Now, in SL2, I can again look at the diagonal matrices, and that gives me there the matrices A inverse. And so I have a natural map from the multiplicative group to the torus, so I have a coroot, an element of homomorphism from multiplicative group to the torus. And there is a natural correspondence between both. If I take a root, I have a corresponding SL2 and a corresponding coroot, and it's a nice big Jackson between the two. And it's one can formulate classification of reductive group, reduce the classification of such system, and the axioms one need to put, one has a completely symmetric role between character and co-character. So one has this xt, so one has a abelian group X, dual Y, a set of roots, a set of coroot, correspondence between the two, some axioms, symmetric between the two, and that is the classification of complex reductive group. And it's this complex symmetry which allow one to define the Langlands dual of a complex reductive group. One first take the group for which one has a torus where the character are this Y and the dual are this X. For instance, GLN is self-dual, symplectic group goes to orthogonal group. Maybe the Giovanni is wrong, but orthogonal group, sorry. And this symmetry will play an important role later when one tells something about representation, and this means something about weights. One can do often a dual statement involving one parameter subgroups. I think that's. Yes, I will still give an example. Oh no, I had one thing to tell in addition. If in X of t tensor with R, one take general half space, one can look at the roots which are on one side of this half space, and this will be called positive roots. So in the case of GLN, it means that one can consider for example, upper diagonal matrices and look at the root space which are only Serre, and so that will be the positive roots. So that I will call the flush. And all systems of positive root are conjugate by the symmetry, so it doesn't matter which one takes. And then an important definition is a particular weight, which is the sum of the positive roots divided by 2. And if I look at the example of SL4, this means that one look at the character, which is one takes A, so it is 4 by 4 here, then one A1 3 over half, A2 1 over half, A3 minus 1 over half, A4 minus 3 over half. So you see there is something wrong. This rho is not always something with integral coefficient, a monomial with integral coefficient, and I will put this under the rug because it's never play an important role. One can think that one has a character of some double covering of the torus. One can also say that if one goes to inside to PGLN, then this will become something correct because then one can multiply by if I think to PSLN, I multiply by the determinant, which is 1 power 1/2, and I get something integral. So this I will put under the rug, but it's not annoying. And also, in relation to the previous thing, if you look at a character, it's really in the advanced group that you want to look at the zero, because the center will act by scalar. So two elements which differ the one to the other by multiplication by the central element, its character will be zero, not in the same time. So the locus of the zero is something one really want to look in the advanced group, and then this problem disappears also. Okay, now I have the 2 minutes to explain Bell's character formula. I think I can now erase a lot. So first, the irreducible representations are classified by their dominant weights. Which is an element of x of t, so that lambda root is positive for the positive cohort. So one has a set of weights and the classified representation. And now I want to give the formula for what is the value of the character on the torus for a given dominant weight. So it's, yes, sorry. And you've forgotten to tell about the Well group. So in this SL2, one has the elements 1, -1 for each root. Which acts on the torus. So one has the action of such element on x of t that generate a finite group, which is the Well group. And one has a character epsilon on W with value in plus or minus 1, where I don't know if I have to put a minus 1 there or not. Yet for the action, yes, for the SL2, it's just transform A inverse to A inverse A. And so one has W acting on x of t, and epsilon is the character of this. But in the case of the GLN, the Well group is the symmetric group permuting the coordinates, and epsilon is the same character of this group. So the formula, one takes there is a numerator and a denominator, sum over the Well group, the value of k lambda of t, sum of the Well group, this epsilon W, so it's an alternating sum over the Well group, T of the power lambda plus rho, divided by the product, yes, first the T minus rho, product of alpha of T minus 1, positive. So some explanation about the formula. One is that for many purposes, it's nicer to classify the representation in terms of lambda plus rho instead of in terms of the dominant weight lambda. Second observation is that you see you have some alternating sum of something over the Well group. So because of that, this expression will vanish at t which are fixed by some reflection. And that's why you can have this denominator which vanish exactly where this is forced to vanish because of the antisymmetry. And now a special case is the case where lambda equals 0, which is the trivial representation where the character is 1. And so it's not a trivial fact that numerator is equal to the denominator, but it gives a nice formula which will be crucial that the sum W lambda C0, divided is equal this T minus rho product of alpha T minus 1. And now, in the case of GLN, this sum over the symmetric group is in fact essentially a determinant. Essentially, you have a van der Monde determinant, and one has to be careful about those factors which will have no importance. In the case of GLN, this is the expression of van der Monde determinant as a product of linear factors.
You need W row there? W acting on rows?
Oh, sorry, yes. Thank you.
W identical. So
Excuse me. Now, a corollary, if you suppose that lambda plus rho equals some multiple of rho, you have a similar formula for the numerator now. Because this formula, if you replace t by tn, it remains true. And then you get a formula expressing what is the sum for tw n rho. So for lambda plus rho equal n rho, we get the following formula. Product of, I will neglect those characters which don't matter for zeros. So product alpha tn minus 1 divided by product of alpha t minus 1. So for those nice representations where lambda plus rho is a multiple of rho, we have a nice product formula for the character, and you see term by term each divides the other, so the locus of 0 in this case is the set of t. So for some root alpha of tn is 1, but alpha t is not 1. So this will be the set of 0. So in this case, the locus of 0 is a number of translated subtorus. And then it's clear that there are plenty of 0 of finite order. But this is not what I had promised. Here I have found a few characters for which I have plenty of zero of Torfen. And what I have promised is for all representation somewhere some zero of Torfen. But now I will use this duality between the two sides. And what I will show is that if I take in y 1 over what I will call rho hat, which is 1/2 of the sum of over r plus of the coroot. So this is a particular one parameter subgroup in the torus, dually to the fact that I have this nice product formula for those special characters on the whole torus. I will have a nice formula for any character on this particular one parameter subgroup. Again, with a product expression which implies some zero of the. So let me do that. The way I like to express is as follows. Let me look at the group algebra of XT. This is functions on the torus. If I have a character is a function, I take linear combination of character, I get function. I am just telling that on something like C star n, the algebraic function, the one I want to consider, from the Laurent polynomial algebra. And this is the group algebra of Zn. So I have here function on T. On the other side, I will look at function on Y, T, and I will make a pairing between the two with bilinear pairing, so that if I take X here and Y there, so X is in X a character, Y is in the dual group, to it I will attach the function on the multiplicative group do what's in power x, y. So concretely, I have, if I fix y here, this y is a one parameter subgroup, a GM mapping to the torus. This is a function on the torus, and this is the restriction of this function to this one parameter subgroup. And this interpretation that this bilinear map on Y is restriction to a GM means that if I take this pairing F, Y, an element there, this will be multiplicative in F. So then you have a product of two functions, I restrict it somewhere, I still get the product of the two functions. Now, by the symmetry of the picture between R and R dual, I will also have that if I fix some X in X of T and I evaluate it on anything, some linear combination of elements of Y, then this will be multiplicative in Y. So there is no difference between the two sides. Now, this being known, let me tell what happens. I will take for X the element lambda plus rho Serre. And I will first consider the numerator of Bell's formula. And so here I take the element W what? And now I can, this pairing is invariant by the action of W, so I can also write it W lambda plus rho, evaluated with an epsilon, evaluated on what? No, sorry. I start again. What I had first is the sum epsilon W and center element lambda plus rho transformed by W, and I want to understand what this character is on this particular one parameter subgroup. Maybe I should tell what this parameter subgroup is. If I take the case of SL3, it will be A1 in, for instance. And now I put the W to the other side. This is this pairing between lambda plus rho and the sum of epsilon W of what. And now I have a product formula for this in the same way that I had this product formula on this side. And what it will give me, and now so it's product thing. So the result is also a product. And what one obtains is that the character of lambda plus rho restricted to rho hat of u will be some inversible factor, which I will not care about, corresponding to this t minus rho there, times the product of u lambda plus rho and all cohorts minus 1. So that is the factorization of the character restricted to the subgroups rho hat. That's for the numerator, but the denominator, I can write it in this form, the same thing. So EIF divided by the product of u rho like that, minus 1. So thus dualizing the argument, which gave a nice formula for a few representation, one gets a nice formula for product type for all representation restricted to this parameter subgroups. And then it's clear that this will be a product of cyclotomic polynomial. It's not trivial because lambda is not 0, because it's not a one-dimensional representation. And so this will prove that on this one parameter subgroup, in fact, all 0 of the character will be roots of unity. And there will be some. So that's for the proof of existence of element of the group where the character vanish at some Torfen element. Now I want to explain why I can find the Torfen element whose order is a prime power. And I have to look carefully at this formula. If I look at corresponding factor in a numerator and denominator, EIF rho and EIF lambda plus rho against some positive cohorts. So this is a sum of rho alpha hat, the same as here, plus lambda alpha hat, which is something positive of 0. And because I have assumed that lambda not 0, sometimes it's strictly more. So you have a product of un minus 1, here not a product of minus 1. The one above are always smaller than the one below, and one at least is strictly small. One has a strict inequality, at least in one case. So it's enough to prove the following lemma. Consider some index set 5, no, call it A rather. There it's the coroots, positive coroots, and consider product u m alpha minus 1 divided by u n alpha minus 1. Suppose that m alpha is at least n alpha, and that sometime you have strict inequality. Then this rational function will vanish, will be defined and vanish at some point of prime power order. And applying it to this formula, one obtains the fact that there is a 0 of prime power order for the character. Now I will prove it after relaxing somewhat to the assumption. I will just assume that the product of the m alpha is bigger than the product of the n alpha. One observation here, things work very well. It's not obvious on the formula that this function is a polynomial. Here, in the general case, it might well not be a polynomial, but I just claimed somewhere it is defined and one has vanishing. Then 0. In this case, I want to prove 0 of prime power of. Now look at this assumption, and for each prime, the biggest power of this prime, which occur in m alpha. So we decompose everything according to prime, and so if I take the L part here and there, for some L, the L part here will be bigger than the L part there. So essentially now I am reduced to the case where m alpha and n alpha are prime power, because yes, I would have still at an element to see whether it is 0 or not, I have to count for, if it is of order k, I have to look at which alpha one has m alpha divisible by k, and the same question here, and one wants not to be bigger than the other, both 0 on the numerator and the denominator. So reduction to m alpha in alpha prime power by taking the L part here, the L part there, and finding some L for which one keeps the same inequality. So now I have to consider product U L R alpha minus 1 divided by product U L S alpha minus 1. And I have the same question. Yes, and what I know is that the sum of the A alpha is bigger than the sum of the S alpha. Now, suppose we wonder about some integer A and we wonder whether the primitive L.'s root of unity are zero of this quantity. For this, we have to count how many numerator vanish on it and how many denominator vanish on it. So we have to consider sum of the R alpha for R alpha bigger than A, and also the sum of the S alpha, but the sum extended only for the bigger or equal, sorry. So this difference will be the order of the vanishing, and we want to avoid sometime positive. Now, if I think to those R alpha after ordering them as a partition, those sums correspond to the transpose partition. So here I have transpose partition A, and here transpose partition A also. Now, the sum of the length of the row partition or of the transpose partition, that's the same. So I have also from this inequality that sum of the transpose partition minus sum for the transpose partition of A is bigger than 0, and this is the sum of T minus S A. This sum is strictly positive, and so one of the terms is strictly positive. So that's the proof. Now I want to make a number of comments. So when one is very naive, as I was at the beginning, one looks at the character, one sees no reason why it would vanish at some Dorfan element, because in general function has no reason to vanish with those very special bonds. And there are theorems to that effect, which I have not had to prove. If on a torus you have a function, and you look at the Dorfan bond on which it vanishes, then it will be a union of translate of subtorus, a finite such union. It was the situation we saw for lambda plus rho being a multiple of rho, and then we have only translate of one codimension one subtorus. So one would like to guess where the zero should be, and here we have one mechanism to finding zero by restricting to this nice one parameter subgroup, which in the case of SL3 is this subgroup. On this subgroup, the character will be a product of cyclotomic polynomial. Now, little by little, I have found more and more reason why something could be a zero, but each time I was looking at V2 and computing some example, I was finding more. So I don't have any conjecture of when one should expect a zero. Of course, there should always be some accident, but one would like to know what are the reasonable zero, what one should expect, even if one cannot prove. So I can tell a few of the things which I have found as reason, but for G2 it does not give everything, and I have no idea what would be a complete list of possible ideas.
You get a growing number of zeros when you increase the weight.
Yes, but already on
That part. But
yes.
you know, if you upper bounds for the number of zeros.
No. And of course, as the case of lambda plus rho multiple of something, then you have infinitely many. I would, if I'm very optimistic, I would hope that, no, that's not the only case, there is not a case like it, but in all cases I know, one has isolated zeros and translate of codimension 1 torus, and you've never seen anything else. So let me, yes, in 5 minutes I can give some of things one can do. So as I was telling, lambda plus rho is much more natural for parameterizing representation than lambda. And suppose that lambda plus rho is a multiple of something. So in those natural parameters, one is m times the other and strictly positive. Then we have this formula, and I will neglect in the formula those term like invertible term like this, which don't matter for zeros. But I could keep them. So here I have epsilon w t w lambda. Oh, sorry. Yes, divided by something. And so this is some epsilon w t power n lambda prime plus rho w of this divided by something also. And this is just evaluating this numerator at c to the power n. So I should still put the something I have erased. I put here epsilon w t w of tn w of rho times the same sum epsilon w t w of rho. So what this formula tells us, except something invertible, is that key of lambda plus rho will be equal of applied to t, will be k of lambda prime plus rho applied to tn times the character for n rho. N minus 1. So when lambda plus rho is multiple of something, this completely reduced to the case when what it is the multiple of. So that's one kind of thing you have. Another kind of thing you have with this is the following. Suppose you have a system of roots like here, and you are in the case where we have 2 lengths of roots. So for instance, so here is 0, and here are the roots of the 2. If you multiply the 4th root by square root of 3, then the old long roots and those multiples of the 4th root form again a root system of type G2. And because of that, you had something nice happening to a summation of for rho, which was the summation of the positive root 1/2. You have the same nice thing happening for 1/2 summation of those roots, the old 4th roots, the old long roots, and the new long roots which were 3 times the previous one. And dually, you can do the same on the y side, and you get another one parameter subgroup rho hat, where we have the same property that the restriction of the character is again the product of cyclotomic polynomials. So for G2, we have a multiplication by square root of 3. For you have also P2, C2, F2, then you have a multiplication by square root of 2 and the same kind of story. So when there are 2 lengths of roots, you have another one parameter subgroup where nice things can happen. So that's 2. Now, another thing is that in the character formula, if you look what happens at some point, you have used that when you had that the locus when the alpha t are 1 are 0 of what happens above. Now, if you look only at Dolphin point, just the same reason will tell you that the sum above will vanish, sometime where there is no root vanishing at it. So the criterion you have to need is that if for some, you have this lambda plus rho, you evaluate it against a coroot, you get some integer, and then at all endorphin bonds, which are not killed by the denominator, it will vanish. So that's a third reason I found. I have another reason I found for G2, but it's a little too complicated to explain. And in my experiment for G2, I found many cases I cannot explain. And I will stop it.
Any questions?
So it seems you're using this lens GM to describe the subvarieties of torus, which is vanishes and then which are translates by.
Yes.
And you're saying you never get anything more complicated than one dimension.
Yes,
one
the only thing I got so far. Maybe this is accessible because one has to differentiate and see if things remain 0,
But that's really what's behind all this. Is that really what's going on here? Is the understanding of that zero set?
Yes, we want to understand which are the torus
which-
on which things happen.
And,
So the transit of torus,
and only the torsion.
yes, and I would expect that when has not lambda plus rho a multiple of something, I would expect it just isolated point which one want to explain, because the nice case it was a multiple. It was n lambda plus rho which was multiple. Otherwise, I only have seen isolated points, some reason for them to exist, and no conjecture for when in general they should exist.
In 30 seconds, how do you go from this case to the general case?
So if your group G, extension of the finite group and this reductive group, and now you have an irreducible representation, so you have some idea of how it will behave. You have this representation V. Here you decompose it in isotopic components. so parameterized by some sets of weights. So each isotopic component multiple of some representation V lambda, and this F will permute the representation occur. So we have this permutation representation of F on this finite set. Now I have to mention this theorem of Liouville, 1883, something like that, that if you have a finite group, you have, yes, and also this action of the finite set is transitive, otherwise the representation would be reducible, grouping together the isotopic part. If you have a group acting on a finite set and it's transitive, then there are parts of the group which act with those fixed parts, with the proviso that E is not reduced to one element. So let us first suppose that the representation V is not isotopic when restricted to V. Then you lift any element of F which acts with those fixed parts, and this will have trace 0. And if you have here an element of this finite group, you can always lift it to an element of tau of an intergroup. Essentially because you can lift it first to the normalizer of a maximal torus, then we have the same question for extension of F by a maximal torus. And so now it remains the case where the restriction to V0 is isotopic. Now, one case is when the restriction to V0 is trivial, and then you have to use Bernstein theorem I was telling. Now, when it is multiple of something non-trivial, essentially you have a projective representation of, I don't remember exactly, but it's the same kind of game. But so the two main theorems to use is this theorem of Verdun, that for a transitive action there are always elements acting with those fixed bonds, and the theorem for just a finite group, there are always elements where characters of course degree bigger than 1 vanish, and then one has to fight a little when this has one element or to represent, and so on. Maybe I can tell, do you want the proof of the theorem of Verdun? Because it's essentially the same as the proof of the theorem of one side. One can view it as a number of ways. You consider a point here, and the stabilizer of this point, you have to show that the union of the conjugate cannot fill the whole of F. And you can't. You have, if they were disjoint, it would be possible that they would just fill, but they are not disjoint, and because of that one has to miss something. And one can express it with character in a completely parallel way as Bernstein proved.
But then to the prime power order, then you have to use the multiplication, right?
Sorry?
But then to get
Oh, yes. Well, if you want prime power, you need the same kind of reduction. So you would need to know that here there are some element of prime power order which has no fixed bond, and you have to know the analog of Bernstein, but also that any character vanishes on some element which is of prime power order. And those are claimed, but who knows?
And to go from reductive to just algebraic group.
Sorry? Oh, no, that's clear because the unipotent radical It don't matter, it has to act trivially because the representation is irreducible.
Okay, if there are no other questions, let's thank Pierre.